Welcome everybody to the ASTRA-sim tutorial online and in person, and I think more people will trickle in as the day progresses. So I'm Tushar Krishna, and I'm happy to be running this tutorial along with Saeed Rashidi, William Won, and Tae Kyung Hyo. We're all from Georgia Tech, and this work has been done in collaboration with Srinivas Sridharan at Meta and Sudarshan Srinivasan at Intel. And this is the broad agenda. So I'm going to kick off things by introducing distributed deep learning training platforms, and then Saeed is going to take over and talk about our framework called ASTRA-sim. Then we'll have the coffee break. After that, William and Tae Kyung will go over some, hands-on demo and exercises of running ASTRA-sim, and finally we'll conclude by talking about some extensions and future development. So the tutorial website is listed here. And the tutorial is also being recorded on Zoom and it will be uploaded. So in terms of installation for ASTRA-sim, if you want to kind of go ahead and get started. So if you go to the ASTRA-sim website and you go to the ISCA 22 and 22 tutorials, this is basically where all the resources are. So you can actually install ASTRA-sim, both the source code as well as, there's a pre-built Docker image as well. And we've also provided links to the GitHub repositories of the code bases that we'll be using. But if you go to the installation, it'll automatically clone the appropriate repositories and the demo exercises. All right, so let's get started. So as I said, again, welcome. So this is going to be the agenda for today. So, the key engine, of course, we're all, here because we know that AI has been pervasive in our lives, right? And the key engine that's been driving the AI revolution has been this notion of training these models, right? So the idea is you have a large model, let's say a large deep neural network, and you give it, many samples, input samples. These could be images, and then you kind of, train it so that it will learn and start classifying or recommending things. And of course, deep learning has shown massive value across vision, language, speech, and recommendation systems. So in the context of machine learning, of course, training can, like, if you really think about training, there's several ways of classifying it. So one notion is, of course, you want to kind of get feedback from data, right? So you can do it in a supervised manner and an unsupervised manner, semi-supervised reinforcement learning, and you can kind of use this across various tasks. So normally detection classification, like there's a lot of tasks for which ML is being used. And in terms of hyperparameter optimization, there's a lot of different ways you can use. You can use stochastic gradient descent, you have rule-based methods, and so on. And this interesting survey article actually does a very good job of talking about a lot of these methods. We are going to be focusing essentially on supervised learning with stochastic gradient descent, which is the most popular thing for DNN. So essentially, when we say training here, really talk about supervised training with SGD. So training essentially consists of three computation phases. There's kind of the forward pass or inference. And then there is the back pass, which includes the weight gradient and the input gradient computations, right? And we'll use a term called training loop a lot of times today. The training loop dictates the order in which we issue these basic operations and possibly their related communication tasks. So the key challenge with deep learning training today is the fact that training time is really becoming large. And the reason is that models are becoming really large. DNNs are large, training samples are becoming larger. If you have things like recommendation models, you kind of have to keep training it with more and more samples. And as we all know, right, Moore's law has ended. So you can't just expect your next generation hardware to just keep giving you, exponential performance increase. So this is a very famous chart that kind of shows how there's been a 300,000x increase in the compute requirement to train from AlexNet, which really kickstarted the deep learning revolution, to AlphaGo Zero, right? The famous machine that actually beat a human in the game of Go. And so large models, as I said here, you have models that are in billions of parameters, hundreds of billions. GPT-3 is very popular, 175 billion, and transformers have already hit 1 trillion parameters as well. And large models essentially mean large amounts of communication. So on the right, we're showing the communication volume that needs to be communicated when you're doing this training. And as you can see, that's also gone up significantly. So the basic idea is, at a very fundamental level, given that these models are so large, and if you imagine like an endpoint, let's say GPU with maybe tens of gigabytes of memory, just to fit the model, you need multiple accelerators. So at a very fundamental level, you need to kind of, run this in a distributed manner just to fit the model. And of course, for performance reasons, you might want to also do that. So as an example, like you need at least 16 neural processing units. That's the term we'll be using for any accelerator. You just need 16 NPUs to even just fit the GPT-3 model. I'm not even talking about, its input samples, intermediate optimizer state. And you need 128 accelerators to, just fit a transformer 1 trillion model. So this is where there's been a big interest in distributed, like deep learning training platforms. So these are specialized systems that are being built just for running the workload of training. Given that training is so important, this is really like a specialized supercomputer, if you will, then optimized for this application. So you want to build customized chips for training. So, GPUs are, of course, definitely an example, which are becoming more and more focused for AI. TPUs are an example, FPGAs and a bunch of accelerators. And now you want to scale the training across more and more compute nodes, right? So the Google TPU v3, NVIDIA's DGX, Facebook Xeon are all examples of such training platforms. And there's many more, right? Like if you've seen the news, so Cerebras CS2 focuses heavily on training. Tesla's Dojo is another machine built especially for training. NVIDIA's DGX then scaled out with Mellanox Sharp switches, Intel's Habana, IBM Blue Connect, all of these are emerging training platforms. So essentially, designing training platforms has become kind of a very important sub area in itself, which kind of borrows from traditional compute architecture and high performance computing. And we'll kind of focus a lot on what some of the interesting challenges here are. So this is what a deep learning training platform looks like from a high level. So a bunch of accelerators at the endpoints. Of course, there's the CPUs, connected by your classic cache coherent interconnect, but you have accelerators that are also connected together by some specialized quote unquote scale up fabric. And then, you can also scale out via NICs, right? Using traditional scale out fabrics like Ethernet, InfiniBand, and so on. So this is what we're going to be focusing on, right? So what are some of the challenges with, systems challenges with distributed training? Communication, right? So inevitably, if you have any distributed algorithm, communication is a challenge. So what does this communication depend on? It really depends on the synchronization schema and the parallelism approach. And we'll talk about this in a bit. And the main question is, well, is it really a problem, right? So is communication a problem? And the interesting point is it really depends, right? So it depends on whether you can hide it behind compute. So as long as you can hide all of your communication very nicely and stage it behind compute, then you're going to probably just be compute bound. And then your kind of, focus should be on the accelerators, right? Which is what we've all been focusing on. But what we'll see is, it's more and more, it's becoming a point where you're becoming more and more communication bound. And that's the challenge that we want to solve. So how do you actually determine whether you're compute bound or communication bound, right? So this really now means that you kind of have to look at the entire co-design stack for distributed training and then understand each aspect and where the bottlenecks are. So my part of the talk is actually going to focus on this stack. So we're going to kind of try to understand what each of the components are that go into, deploying a model in a distributed manner. So at the very top, you have the actual DNN model. Then you decide on a parallelization strategy for it, the communication policy and pattern, then some framework level scheduling. And then you kind of have the actual compute and memory system, right? So the accelerators and the memory system, the communication mechanism for scheduling your compute and communication. And finally, like, low-level network related thing, right? So the messaging and transport layer, endpoint design, the fabric design and network implementation. And what we've done, courtesy with our collaborators is actually try to divide this into 3 broad categories, like the workload layer, the system layer, and the network layer. And the reason for dividing this and this coming up with this abstraction is also to kind of, allow innovation at each level and, have this interesting tussle between doing co-design while maintaining abstractions. So this flow is what we'll be trying to understand in my part of the talk. So let's start at the very top, right? So we want to train a model. So of course, there's different kinds of models we might want to train. So there's, vision models like ResNet that are very popular. Transformer models are extremely popular for NLP and, recommendation models like DLRM, right? So from the perspective of, distributed training, what we really care about is, the layer types that will emerge from each of these models. So ResNet will probably have many convolution layers, some few fully connected layers. Transformer models have several attention layers and fully connected layers, and DLRM has fully connected layers and large embedding layer. And you care about the parameter sizes. As I mentioned, these could be from millions to trillions. So this will really kind of, determine, like, really be the first step before you start thinking about deploying this. So once you have the model, now you need to start thinking about how you actually, run it in parallel, right? So essentially the parallelization strategy is the way with which the compute task is distributed across different compute nodes. So as I said, there's hundreds or thousands of accelerator endpoints. So you could either, take your actual data samples, like, and split the mini batch. This is called data parallel. Or you take the model itself and split it. And again, in some cases, these are like choices. In some cases, it's inevitable. As I mentioned, if you have a very large model, you have to split the model. There's no way it will not even fit in the device's memory. So that's called model parallel, or you could split the DNN layers and run it in a pipeline manner. That's called pipeline parallel. And the parallelization strategy also defines the communication pattern across different nodes. So for example, data parallel training looks like the following. So suppose I have two accelerator nodes. I'm going to distribute the data across multiple nodes and replicate the model, right? So I split the data samples across nodes and replicate the model. And since every accelerator has the copy of the model, during the forward pass, you're just running a few data samples through the entire model, which is very classic inference, and there's no communication actually needed between any of the accelerators. But during the backward pass, since each of these is only calculating error gradients for part of the data samples, you actually need to communicate in order to kind of update the entire model. So you actually have to communicate the weight gradients during the back pass, and this communication is happening in a non-blocking manner here, right? You basically communicate and like go all the way here and then start the next iteration. In model parallel, you actually split the model. So now each accelerator has a copy, like just a partial part of the model and all of the data samples. So even during inference, since you're only running your data samples to part of the model, to actually get the output activations, you have to communicate at each during the forward pass as well. And this is a blocking communicate. You actually need to wait for this to finish, and then you communicate so that you get the next the output activations, which become the input activations for the next year and so on. And so there's communication in the forward pass, and there's also communication in the backward pass. Here you're communicating the input gradients, right? So model parallel, as you can see, has a lot more communication. There's also like hybrid parallelism schemes that are often used. So one technique that's often used is, let's try to do model parallel up to a certain point, because we have the model is very large. So suppose the example I gave with a GPT-3, I kind of have to do model parallel across some set of nodes, let's say 60 nodes. And then if I have a larger system, I do data parallel across this, right? So now here, this is purely for scalability, while this one is kind of necessary. So there's hybrid parallel schemes that are often used in many systems. And pipeline parallelism is also gaining a lot of popularity. So in pipeline parallelism, you essentially distribute the DNN layers across all the nodes. So you kind of decompose the mini batch into micro batches and then propagate them through the pipeline. So now again, you're going to communicate the outputs during the forward pass, just like you did in data parallel. So here you have to do it because the next layer is being run by the next accelerator, right? So you communicate. And this is a blocking communication. And in the back pass, again, you have to communicate the input and weight gradients. So pipeline parallelism is again very interesting. You kind of have to break a mini batch into micro batches, fill the pipeline, and once your pipeline is full, you kind of get good throughput, but you kind of have the classic problem of bubbles in the pipeline as well. So essentially, I guess where I'm going with this is each of these parallelism schemes has kind of its pros and cons. Like, in some cases, in some situations, it's nice, but each of them has its cons, right? So here there could be bubbles. In some cases, there's a lot of data being communicated. In data parallel, you just have a copy of the model being replicated, so memory requirements go up and so on. And so there is, of course, a need for more and more sophisticated schemes, right? So models are becoming larger, compute not at the same rate. And so, once you get to these trillion parameter models, identifying the right parallelism scheme is an open research problem in itself. And so here, there's been interesting techniques that have been proposed. So Microsoft Zero is this technique that Microsoft proposed, which was essentially kind of looking at the fact that, of course, you're doing model parallel to, to essentially like split the model. But the problem is that in addition to the model state, there's also a lot of intermediate optimizer state that takes up memory. And so you actually have a huge memory overhead because of the optimizer state. So zero was this interesting technique where you actually partition the optimizer state and the gradient state as well. So it's not just the model weights, but the optimizer and gradient state is also partitioned. And it has this interesting knob where you can trade off, amount of communication and memory requirements. So you partition this, so you increase communication, but now you have a lesser memory requirement. So again, these are like interesting hybrid schemes that are being proposed. Facebook's DLRM is another interesting, hybrid parallelism scheme where the identification is that embedding layers are really large. So embedding tables are really large. So for embeddings, let's do model parallel, while for the MLP layers, let's do data parallel. And this again means, there's interesting implications in terms of communication. So you essentially have the output activations being communicated here, but you then have to do an all-to-all communication. I'll describe what this means in a bit. And then you, of course, on the MLP layers, you are running data parallel. So again, you have output activations just going one after the other. And if you're familiar with the DLRM architecture, this kind of, the bottom half and the top half of the MLP layer. So once you're done with the bottom half, you actually have to, do this all-to-all synchronization here. Once this finishes, then you run the top half. This is all the forward pass. And during the backward pass, again, you're kind of communicating weight and input gradients. This is just classic data parallels. I'd mentioned, weight gradients will have to be reduced. And so this happens. And again, once the top half ends, you have an all-to-all that you have to run with the embedding layer. So DLRM introduces, again, very, very interesting communication scenarios because of the parallelism scheme. And there's even more sophisticated schemes, Microsoft's Pipe Dream, NVIDIA's Megatron. This was an interesting article a few months back where, NVIDIA talked about how they used like Microsoft Deep Speed method and Megatron to train the Turing NLG model, which has 530 billion parameters. So essentially, people are developing very, very interesting, schemes to manage the memory overhead and the amount of communication, right? That's kind of the main thing I want to convey here. Okay, so then once you've kind of decided a parallelism scheme, you now need to kind of, actually think about how this communication is being orchestrated. So I'm just trying to remove this. So now kind of, depending on the the parallelism scheme, as I mentioned, input gradients, weight gradients are actually being communicated. So here you kind of have two broad approaches. So you kind of have the actual synchronization scheme, and which is asynchronous versus synchronous. I'll talk about that in a second. And then the communication handling, which could either be parameter server or collective based. And the idea is really to, see whether you can do this in a centralized or a distributed manner. So just to kind of give an example, so synchronization scheme really decides when the node should exchange data, right? Should you wait for all the nodes to complete and then synchronize, or should you have this communication be done in an asynchronous manner? So we'll focus on synchronous training. That's the one that's most popular, but asynchronous training also has, and so in asynchronous training, you can imagine that, some nodes are working on old stale gradients from the previous iteration. Some of them are working on more recent gradients, but, people have shown this techniques like Hogwild that have shown that even then you can actually get to convergence. So it's an interesting research technique, but I think in practice, synchronous training is the one that's used. So that's what we'll be focusing on. And the other mechanism to worry about is, how do you actually orchestrate this communication, right? So I talked about, okay, input gradients being shared, being communicated, weight gradients. Either you could have some centralized parameter server that manages all of this. So parameter in the, so each node will basically send its gradients to the parameter server. This will do the actual reduction, adding everything up, and then, just broadcast it back to everybody for the new iteration, right? So this is a very kind of natural way of doing this. You all compute in parallel, you do your computations in a model parallel or data parallel manner, communicate to the central node, it will do the updates and then send everything back. But of course, this is naturally not very scalable. So this is why I think there's a big interest in trying to do everything in a distributed manner. So this is where like a pure distributed scheme is what's known as a collective based scheme. So here, rather than having a centralized parameter server, all nodes are directly talking to each other and doing like a global reduction of the parameters. And so here you actually use collective communication patterns, right, which are popular from MPI. So broadcast, scatter, gather, reductions. And essentially what you do is like the specific requirement of which collective algorithm is run depends on the parallelization scheme. And as I said, it's either handled by some collective communication mechanism that the system supports, or the collective communication is broken down into individual send and receives, right? So you essentially, like, you can either have some library that lets you orchestrate everything, or you break everything down into, okay, I'm going to send a message here, then you send, which is kind of overall implementing a collective scheme. So so this table just kind of summarizes when collectives are needed. So if you're doing parameter server versus collective, this is summarizing what I mentioned so far. Depending on the parallelization scheme, what kind of information is actually being exchanged. So this kind of comes to the main part, right? So collective algorithms are kind of at the heart of distributed training, right? When you're doing if you're not using a parameter server. And so this is kind of mathematically what each of these patterns does, right? So reduce scatter will essentially, as the name suggests, like do a reduction and kind of scatter the outputs here. So each of you has like a partial part of the gradient. At the end of a reduced scatter, node 0 has the summation of all of like one part of gradient. Node 1 has the second, node 2 has the third, and node 3 has the fourth part, right? And then all gather is where you kind of use this information and just broadcast it to everybody. So again, just the name suggests, like you're kind of gathering this. So at the end of all gather, all these nodes, like you've essentially broadcast this value of like this part of a gradient to everybody. X1 has been broadcast to everybody. And so all reduce is really reduce scatter plus all gather, right? So each of you has some part of the gradient that you accumulated. You're going to, do a reduce scatter to accumulate that part, and then do an all gather to broadcast it to everybody. So all reduces, that's why one of the most popular patterns, which can be broken down into these two components mathematically. And all to all is where you kind of, again, you're just, as the name suggested, you have copies of gradients that you're sending to everybody. And so this is usually done, in model parallel, as I mentioned, especially for the embedding layer in DLRM. And for each of these, there can be different implementation algorithms. So for doing a reduced scatter, there's different kinds of implementation algorithms for all reduce. And these are often known as topology-aware algorithms that I'll mention in a bit. And so again, like kind of keep in mind that there's kind of the algorithm itself, and then there's its implementation. And these implementations are very system specific. So just as an example, this is what a ring-based all reduce looks like. So if I have, let's say, some chunk of data that I need to reduce, and if I have 4 accelerators, let's say these are 4 GPUs, I will actually break that chunk into 4 messages. And the way all reduce will work is in the first phase, the reduce scatter phase, each accelerator will just send, a part of the data to its neighbor. So node 1 communicates, message 1, node 2 communicates message 2, node 3 communicated message 3, and node 4 communicated message 4, right? So each of them in parallel was able to send a message without any contention in a ring. And then in the next step, and you, of course, once you get the message, you add it to the local gradient, local value that you have here. And then, you continue this. So now this sent 1 again, this sent 2, this sent 3, this sent 4. And finally, this sent 1, 2, 3, and 4. So at the end of this step, reduce scatter is done. Everybody has received, the like part of the message and accumulated it locally. So this is where reduce scatter is done. So you've kind of reduced a part of the gradient, but this is, like 1/4 of the message, right? The entire chunk needs to be with each accelerator to essentially get the full model. And so now you do an all gather, basically, which is a broadcast. And again, you do it in the same manner, right? Each of you just takes the value and forwards it to the neighbor. You take the value, forward it to your neighbor, and so on. So you keep doing this over 4 steps. And at the very end, all gather is done, and effectively all reduce is done. So the beauty of this is, there was no contention. You just kind of forwarded a part of the data to your neighbor. They added it up, forwarded, and so on, right? So it's a very elegant way of implementing all reduce if you have a ring-based topology. Of course, if you actually have an all, fully connected topology, this is what a lot of accelerators have, at least at a small level, you can imagine that they're all connected together. Then you don't need to do it in these steps, right? You can in one step just do an all reduce scatter by sending, all parts of your gradients, have these added up. And then in the next step, just simply do a broadcast to everybody because you all to all links and get an all gather. So this is a direct all reduce. And similarly, if you have all like direct links, you can do an all to all also in one step, right? So here in one step, we've basically done an all to all. Of course, this is for, these are for simple topologies, right? You have a ring or you have a fully connected topology. But you can imagine that if you're building an accelerator system that scales up to thousands of nodes, you will probably have more sophisticated topologies, right? So for example, like this is, let's say, an example of something like the Google TPU platform, where you have a 3D torus, right? So you might have a bunch of accelerators on the same chip or on the same package. So I believe TPU V3 has like 4 of these accelerators on the same chip. And then you're connecting them again via a 2D topology here. Or NVIDIA's DGX2 might look like this, a bunch of, let's say, GPUs on a package, and then all of these are connected via NV switches. So here the challenge now becomes that you have heterogeneous bandwidth, right? So the bandwidth you get on chip or on package might be different from the bandwidth you get on these kinds of links like NV links. And so what that ends up meaning is that the collective algorithms I described are also run in a hierarchical manner over multiple phases. So this is an example of a hierarchical all reduce, where you'll first do a reduce scatter in like locally within the package, then all reduce across the rows, then all reduce across the columns, and then again and all gather within the package. So you're trying to make sure that these higher bandwidth links get more communication, lower bandwidth links get less communication. So these kinds of hierarchical algorithms exist, which are again quite interesting, but it again means that you need to be very clever about how this is scheduled across all these bandwidths. Okay, so that's kind of the workload layer, right? So now if we move on to the compute and memory design layer, the compute that you care about in deep learning is typically a matrix multiplication, right? So that's the most dominant part. So you have a matrix multiplication in the forward pass, and the gradient computations also map to matrix multiplication, and which is why this is just some data showing how much these matmul operations dominate in deep learning. And it's not surprising that NVIDIA GPUs have started adding tensor cores, in like CPUs have started adding tensor cores. You have architectures like like the TPU and a bunch of systolic architectures that are all optimized really for matrix multiplications. So the key feature is specialized support, right, for these gems. And essentially, of course, here there's interesting challenges that on the training and compute accelerators face. So a lot of times these gems are not very regular. They're quite irregular, especially when you have gems on the backward pass. And so this means that, so this is a challenge to kind of get high utilization from your accelerator. Gems are also becoming more and more sparse. So models are becoming sparse. So either you have sparsity simply because, of things like dropouts and ReLUs, or you have sparsity because you explicitly imposed it during training by making some weights go to 0. So all of this is, of course, adding challenges on the compute end, right? And so this is just kind of talking about the fact that if I take a gem, map it onto an accelerator like a TPU, depending on the shape of the gem, I might get different kinds of utilization. So if I have this very nice regular flow crossroad gem mapped on this accelerator, I might get 100% utilization with like this nice simple communication through the accelerator. But once I have irregular gems, my utilization drops. And if I have sparse gems, utilization drops even more. So this is a key challenge that accelerators are facing. And there's, again, a lot of active work, if you're familiar with it, on just, handling irregular and sparse gems. So essentially the way to handle irregular gems is, rather than a large array, let's just have multiple smaller arrays, right? So you can imagine like the NVIDIA design. I mean, even though of course overall microarchitecture wise, the GPU is very different from the TPU. I mean, from the perspective of the accelerator component, you can imagine that the TPU is like this very large systolic array, while, NVIDIA's tensor cores are many, many tiny systolic arrays all distributed. So they are naturally useful, to kind of, get better utilization. So of course the trade-off is data reuse versus utilization. For sparsity, there's structured sparsity support that's already been added in GPUs, like NVIDIA's A100 is an example, and unstructured sparsity support is also something a lot of custom accelerators have talked about. So almost every sparse accelerator talk that you'll hear at ISCA is probably going to be on unstructured sparsity, right? So it's a very, very active area of research. So what does this mean from a training perspective? So I think the interesting implication is this whole notion I mentioned about compute versus communication and communication overlap, right? So if your compute is just inefficient and you have a lot of underutilization, you're naturally going to be compute bound because, you're probably going to be memory bound because you're not getting, enough reuse and so on. But ultimately, from the endpoint's perspective, the compute is taking so long that there's not a lot of communication, or the communication is nicely hidden behind it. But if your accelerator becomes more and more efficient, then the challenge is that, communication starts becoming exposed. So this is a growing problem. So this is some experiment we did with the simulation platform, where we said, okay, what if my compute, efficiency becomes 2x or 4x? We noticed that the compute time really drops, of course, but now communication can start becoming challenging. So this is, I think, again, kind of a thing to keep in mind, where increasing the efficiency of the compute accelerator actually has challenge implications on the communication. Okay, so that's on the compute side, right? So now in terms of the actual communication, I mentioned this briefly already, that the way you actually schedule the communication, and this is usually done by libraries like, NVIDIA's Nickel, and so on, where you will essentially, looking at the underlying topology, you will use a topology-aware collective algorithm. So if you have an underlying ring topology, you will naturally try to use a ring-based algorithm. Of course, this is a logical algorithm. You can run a ring-based algorithm on any topology, but in some other topologies, it might lead to congestion. But if you kind of have that kind of a topology, there's these topology-aware collective algorithms. If your topology is actually fully connected, a direct, all reduced algorithm might be better. If your topology is a switch, then halving doubling is this interesting algorithm that tries to, extend data in logarithmic number of steps. And that's the most optimal topology-aware collective algorithm. And then you kindly come into scheduling, right? So, okay, so so again, just kind of going through the start, right? So in the communication side, once I've decided the specific algorithm I'm using, ring-based, halving, doubling, and so on, now I need to schedule these collectives on the links, right? Cycle by cycle. And as I mentioned already, right, you kind of have this hierarchical communication that's happening, especially in these large scale systems, where you might like take the all reduce, break it into pipeline stages, do reduce scatter on the local dimension, then across, then all like, reduce scatter all gather on the rows and columns, and then finally back on the local dimension. The challenge with this is that, the amount of, remember, like every time you're doing an all reduced, you're kind of accumulating messages, right? So the message size kind of decreases as you keep doing all reduces. So the idea is, as you kind of go through this hierarchical all reduce, the size of the messages essentially reduces. And then, of course, once you start doing all gather and broadcasting it, the size of the message goes back, right? And so this has very interesting implications on the amount of delay it takes on the network, right, for each of these pipeline stages. So this is an example of how running a hierarchical all reduce on a topology like this will have variable pipeline delays, which means that your network might be heavily underutilized or oversubscribed, right, for certain dimensions. So how do you manage this efficiently? Like you might have a lot of different idle times. And this is actually a growing problem, especially as you get to larger and larger systems. So this is actually something that we've looked at actively, and we actually have an ISCA paper on this in the main session. So if you're interested, do check it out. It's called Themis. And the idea is to essentially identify this problem of network underutilization, and it's a scheduling scheme that tries to balance across all of these stages. So again, feel free to check out the main paper, and I'll see you all in that talk as well. Okay, so now we kind of come from the system layer to the actual physical network, right? So now that we've kind of, managed all of this scheduling, managed the topology-aware collectives, the scheduling, and so on, at the physical network layer, of course, I'm not going to, there's also the transport layer, which will come in, especially if you're doing, scale out with NICs, you might to worry about TCP and RDMA, but then you come to kind of, lower level endpoint network design. Here, there might be interesting implications so there might be interesting implications of the endpoint design, right? So imagine like an endpoint accelerator where you have many, like, this might be a GPU with many of these SMs, and you have some interface. This is just accelerator fabric interface that communicates with the accelerator fabric, and of course, also communicating with memory. One of the challenges now is, you have a lot of actual compute operations because of the deep learning training, which is all the gems I talked about. But you also have, computations because of the communication operation, right? So all reduce will involve a lot of additions and reductions. So once you kind of schedule the compute and the communication related tasks on the same accelerator, you now start getting into interesting challenges where you're sharing the same accelerator codes. Like some of them are running the actual compute, some of them are managing communication, which naturally means even memory bandwidth gets contended between the actual compute and communication related tasks. And this is actually results from a paper we had at ISCA last year, where we were showing that, scheduling all of this together on the same endpoint GPU actually leads to slowdowns because your memory bandwidth is being heavily contended. And so what we proposed was this interesting accelerator called ACE, which is essentially like a offload component that sits next to the accelerator fabric interface. And it's managing all of the communication related tasks, while the actual accelerator compute can be used for the actual computation task, right? And so the memory bandwidth is also now fully utilized by the compute. So as I mentioned, right, models are becoming larger, the compute capable, like they have less reuse. You really want to use this memory bandwidth for that component and try to have a separate accelerator component for managing the communication, right, with some interesting scratch pads. So again, if you're interested, this is a paper you can check out called ACE. So this is again an interesting example of how, managing like communication compute overlap and how some of the sharing has interesting implications on memory bandwidth and the network bandwidth. Of course, there's alternate approaches to solving this issue. There's another paper that NVIDIA had back in ISCA 2020, where they identified a similar problem, and their solution was to actually try to offload this onto an NV switch, right? So again, I think trying to do collective offloads is a very, very active area of research. And the reason is that, as I mentioned, right, collective communication itself involves a lot of interesting orchestration and computation. And so using your accelerator endpoint for that can actually lead to a lot of inefficiencies. So then you kind of get to even lower level, like the actual. So, okay, so we've kind of talked about the endpoint. Now let's look at the actual network, right? How do you design the network and its topology? So again, right, you might have, let's say, a 3D topology like this. Let's say a torus topology like this, sorry. So if you are a system designer, right, and if you are, let's say, Google, and you want to design the next cloud TPU topology, you can actually kind of, again, like look at different kinds of topologies and try to understand what kind of challenges exist when you're running things like all reduce, right? So this is just some data we collected using, again, ASTRA-sim, where we were looking at, for the same number of nodes, let's say 64 nodes, if I develop like a 1x64x1, right, which is basically a large 64 node ring versus a 2D topology with, 8x8 nodes, or a 3D topology with 2x8x4 nodes or 4x4x4, and I'm running all reduce of different sizes, what are the implications in terms of overall communication time? And the interesting thing here, as I mentioned, is especially when you're doing hierarchical all reduces, the amount of data being communicated changes as you go from dimensions, right? So this again has interesting implications on the number of nodes per dimension. That will affect the amount of data being transferred as you go through dimensions. So sometimes just adding a dimension, depending on the algorithm, might increase the amount of data, decrease it. And so you really need to kind of understand and trade off all of these, right? So in an HPC system, typically you just try to go with a very, uniform multi-dimensional topology. But here with deep learning, given that we know the kinds of communication algorithms are things like all reduce, we can really try to optimize the system more for that. If you have an asymmetric topology, right? Again, I mentioned that bandwidth is not going to be the same in all the dimensions, right? You might have more bandwidth on package because of chiplets. You might have then like somewhat lesser bandwidth because of things like NV links. And then once you go to Ethernet and InfiniBand, even lesser bandwidth, right? So here you have different bandwidths, you have different kinds of choices for the all reduce algorithm. Again, all of this has interesting implications. So I'm not going to go into the data here, but the idea was that this is a challenging co-design space where, given that you're tuning the algorithm and the system architecture, there are different implications. And in some cases, communication time can really, really start dominating. So you need to be careful. And finally, so we've talked about topologies. If you go down even lower level to the actual network implementation, right? So if you're a network designer who cares about, okay, how do I size the buffers and how do I manage congestion and arbitration schemes inside and like at the link level and at the switch level, this is another experiment we had done where we were looking at different kinds of Systems, again, all of them, connected via, let's say, a large switch, either hierarchical systems or like a flat topology. And we were trying to experiment with, the size of the switch buffer we would need. And, especially if you're running, some things in a scale out manner with TCP/IP. And again, what we identified was, depending on the topology itself, if you have a flat topology versus a hierarchical topology, and you have different sized switch buffers, the amount of exposed communication can vary quite a lot. So again, like the tool ASTRA-sim that we have that we'll talk about can be used for studies like this as well, to really like size different network components and see what is most optimal. Okay, so this is basically the summary of the full distributed training stack that I talked about, right? And again, this is kind of, it's nice to, as I said, think about distributed training in the systematic manner as these different layers, because now you can actually optimize each of these layers independently, or given that certain things are given, you can see what's the best implication here, right? So if you really have a fixed system, you can't do anything, then you really want to focus here on trying to optimize and find the best parallelization strategy and probably the best algorithm. But if but if you're an architect, you might be operating at this layer where you're really thinking about either designing the compute and memory system or the network, and see how that works given models today and the expected trends. So how do you navigate this codependent design space? This is why we actually built this simulation infrastructure. So ASTRA-sim essentially takes this co-design stack that I mentioned and implements it, right? So it models these three layers faithfully, like the workload layer, system layer, and network layer. So the workload layer is where you are actually going to define a training loop. As I mentioned, the training loop is really going to define the model and the parallelization strategy and the communication policy together. Then it interfaces with a system layer, which is similar to a library like, as I said, Nickel, where you're going to be managing the actual collectives and which topology of a collective algorithm to use and how do you schedule it. So as I mentioned, this paper that we have, Themis, would essentially fit here inside the scheduler. And then you actually interface with the actual network, and we provide like a network API that will help you interface with different kinds of network simulators. And you can have you can model this in various levels of granularity. So if you are a network designer, you can plug and play different network simulators and study the implications for the whole of this, right? So as I mentioned, just to summarize it, so the workload layer currently supports data parallel, model parallel, and hybrid parallel training loops. These are provided. It's extensible to more training loops, and we're actually also working on a graph-based input format that will allow you to specify arbitrary training loops, including pipeline parallelism. On the system layer, we actually provide support for ring-based, tree-based, all-to-all based, and multi-phase collectives. We provide variety of scheduling policies, and the compute times are actually fed in via an offline simulator that essentially, basically, it kind of gives you the margin, right? If you know amount of compute time, then you can accordingly see how much communication time there is. If communication time dominates, that's exposed communication. If it is less than compute, then you're compute on. So that's kind of the kinds of things it does at the scheduling level. And at the network side, as I mentioned, through the network API, you can plug and play different kinds of network simulators, which allow you to model different topologies, flow control techniques, link bandwidths, congestion control, and so on. And these are all plug and play. So that's I would say the real beauty of this. So you can actually plug in your own model as well. So right now we have an analytical roofline based model that we plug in, and that's what for simplicity we'll be using for a lot of the demo exercises today. We also support Garnet, which is the network model in Gem 5. So essentially we've plugged out Garnet from Gem 5, and this Garnet kind of models, chiplet based systems and heterogeneous bandwidths and so on. So that's, if you're interested in that space, Garnet is the network model to use. And we also have a couple of other network models in development that we'll briefly talk about. So ASTRA-sim essentially now reports end-to-end training time. It reports the communication time for each communication operation. It actually tells you the amount of exposed communication, the exposed communication total computation, and it'll also give you detailed statistics like average message latency per hierarchical collective phase, right? And so this is what ASTRA-sim, in some sense, like this part reports. And then each specific network backend, of course, might have its own specific reports like bandwidth utilization, protocol statistics, switch buffer usage, and so on. So just to summarize, like large model training is an ongoing and open research area. Many emerging supercomputing systems are being designed specifically for this problem. and co-design of the algorithm and system offers high opportunities for speed up and efficiency.